Tonight, we're going to explore one of the most honest and sobering questions in human exploration. The place is Mars, the next world out, and the question is what it would take for a person to survive there. The picture most of us carry is a gentle one. Domes and gardens, warm light, a soft red sunset over a new human home. But the real place is something else entirely. A long, quiet catalogue of separately lethal conditions, hostile in every direction at once. The air is too thin to keep a person conscious. The cold can freeze the atmosphere onto the ground. The soil is laced with quiet poison. It is the honest aftermath of a world that once had rivers and air and lost them. By the end of tonight, you're going to understand why that thin air and cold are only the first entries on a long list. How a crew would build air, water, and warmth from a world that gives none of them. And why this brutality is not a wall, but a row of problems already being solved. Before we get started, take a second to like and subscribe if you enjoy these videos. It really helps a lot. Now let's begin. Picture it the way most people do first. Rounded domes catching amber light. Green rows of vegetables growing under glass. A soft ochre sunset settling over a quiet street in a colony that already feels like home. That picture is gentle. Is also almost entirely wrong. Not a single wall to climb. Dozens of hazards, standing shoulder to shoulder, most of them present everywhere on the surface, all the time, waiting. But here's where it gets strange. That same brutality turns out to be calming once you understand where it comes from. None of it is arbitrary. It is the long, honest consequence of physics, of biology, and of a planet that once had far more than it has now and slowly lost it. It has sat out there exactly this hostile for billions of years, and it will still be sitting there tomorrow morning. There is no urgency in any of it. Nothing is coming to get you faster because you take the time to understand it first. That patience is the whole tone of what follows. Every hazard in this catalogue has been waiting the same amount of time, and every one of them can be understood before it has to be faced. Start with what the place actually is. The next world out runs roughly half the width of the world you call home. If your home were a full dinner plate, this one would sit closer to a saucer. Its mass comes in at about a tenth of what you're used to, and the pull it exerts on a standing body follows suit. A person who weighs 100 pounds at home would weigh close to 38 pounds standing on that ground. Light enough to notice with every step, not light enough to feel free. The sky overhead runs faintly pink and orange instead of blue, tinted by fine dust suspended high in a thin atmosphere. The land below is cold, dry, and dusty, crossed by the dry beds of rivers that stopped flowing long ago, channels carved by water that is not there anymore. None of that alone would kill quickly. Here is where it turns serious. The air is so thin that an unprotected body would lose consciousness within seconds of stepping into it. Temperatures swing from cold enough to freeze the atmosphere itself onto the ground at the winter poles, to something almost mild on the warmest afternoons near the equator, and back down again by nightfall. The soil carries compounds that quietly disrupt the human thyroid and kill most candidate crops before they take root. Sitting in the dust under every footprint anyone will ever leave there. And the only breathable oxygen anywhere on that world is whatever machines that do not yet exist at crew scale can pull out of the ground and the thin air itself. Cold, airless, laced with quiet poison, none of it dramatic on its own, all of it lethal together, and all of it waiting at once, not lined up to be handled one problem at a time. Getting there turns out to be its own catalogue entirely. One written in pure orbital arithmetic instead of biology. The next world out circles the sun about 1.5 times farther out than home does. So sunlight reaching its ground runs less than half as bright as the sunlight you grew up under. One full circuit of the sun there takes roughly 687 days. nearly twice the 365 the homeworld needs. And because the two planets move at different speeds on orbits of different sizes, the gap between them never holds still. It stretches and shrinks on a slow, repeating clock that neither planet asks for and neither can change. At their closest, an alignment astronomers call opposition, the two worlds can close to somewhere near 34 million miles apart. An airliner flying non-stop, never landing, never refueling, would still need something like 7 years to cross that distance. And that is the two planets at their most cooperative. At their farthest, with the sun parked directly between them, the gap stretches past 240 million miles. A flight that would eat most of a human lifetime, 7 times over. Only one part of that constantly shifting distance is ever worth attempting. A fuel-efficient crossing needs both worlds lined up in one specific geometry, and that alignment repeats roughly every 26 months. It stays open for only a few weeks at a time. Miss it, and the wait for the next one runs past 2 years. Here's the part most people get wrong. Surely a bigger engine and more fuel could just force the issue and leave any time, on whatever schedule suits the crew. It cannot. Carrying fuel to lift more fuel is an exponential problem, not a simple one. Add propellant to force an unfavorable path, and the trip does not get faster. It means a heavier rocket, one that can no longer lift itself off the ground on the one low-energy route the planets actually allow. Not a convenience. The only path the mass budget can survive. That arithmetic has held for more than a century of hand-calculated rocket equations, through every generation of engine and every design of spacecraft, and it has never once bent to make room for an impatient departure. The planets set the calendar. The engineers only get to read it, then wait for the date it names. So the crew leaves on the planet's schedule, not their own, and once they leave, they're committed for a long while. The crossing itself takes 6 to 9 months, and almost none of it is flying in any active sense most people picture. Engines fire hard at the start and then fall silent for the rest of the journey. What follows is coasting, drifting along one long curving ellipse, bleeding slowly outward from one orbit until it intersects the next world's orbit at the exact moment that world arrives at the same point in space. Neither still nor really moving, by any measure the crew inside can feel. There is no sensation of speed at all, no rushing scenery, no wind, nothing outside the window but slow, silent stars in fixed positions, night after night, for months. There is no stopping part way, no turning back, no stepping outside for air. For 6 to 9 months, a small crew sits sealed inside a single vehicle in near total silence, surrounded by nothing but their own air, their own water, their own food, and each other. Whatever they packed is what they have. Whatever breaks, they fix, or they live without it. That is the trip before anything on the ground has had a single chance to try to kill them. And that was only the first entry in a much longer catalogue. That long quiet is not empty. Inside it, something is already happening to the crew, and it has nothing to do with the stars outside the window. The human body is, in a deep and literal sense, a machine built for a world that pulls on it. Hundreds of millions of years of evolution shaped every part of it around one constant force pressing down. Bones hold weight because there has always been weight to hold. Muscles push against gravity because there has always been gravity to push against. The heart moves blood upward against that same pull every second of every day without being asked. Even the inner ear, the quiet system that tells a body which way is down, was built assuming down would always be there to find. Take the pull away, and the body does not relax into some weightless kind of freedom. It begins, calmly and methodically, to take itself apart. Not through failure, Through economy. Living tissue is expensive to keep running. Bone costs calcium and mineral. Muscle costs calories, hour after hour, whether it is used or not. A heart shaped to fight gravity costs more work than one that no longer has to. The body follows one rule it has kept for millions of years. Keep what gets used. Let go of what doesn't. Remove the demand, and the body reads the silence as permission. In a place with nothing left to push against, muscle becomes a luxury. In a place with no weight left to bear, so does bone. The body is doing exactly what it has always done. It is only doing it somewhere it was never built to do it. Start with the skeleton itself. In the regions that normally carry weight, the lower spine, the hip, the long bone of the upper leg, density falls at somewhere between 1 and 2% every single month. 6 months into the crossing, a returning crew member carries measurably less bone in exactly the places that would once have taken a body's full weight with every ordinary step. Ground-based rehabilitation afterward can recover much of what was lost. Not quickly, and not always completely. Some of what the body let go of during those months, it does not fully take back. The muscles follow the same quiet arithmetic. The ones that hold posture and drive movement, the legs, the lower back, the deep muscles of the core begin shrinking within weeks, not months. Long-duration crews spend roughly 2 hours of every working day fighting this directly, strapped into machines built to simulate a resistance that isn't naturally there anymore. 2 hours, every day, for the length of the whole crossing. And even then, measurable loss still happens. The body has already decided the old size isn't needed, and 2 hours of pretending otherwise slows the decision without reversing it. The heart changes too, more quietly than either. Without a standing column of blood to push upward against, it gradually rounds, losing the slightly elongated shape built for pumping against a vertical pull. Its walls adjust to a job that suddenly asks less of them. Blood, and the fluid that bathes every cell in the body, drifts upward instead of pooling low, away from the legs and toward the head, which is why long-duration crews come home with the same faintly full, congested look in the face. A small, strange souvenir of months spent going nowhere in particular, at considerable speed. But here's where it gets strange. That same upward drift does not stop at the heart. It reaches somewhere it was never supposed to go. The clear fluid that cushions the brain and spinal cord shifts upward, along with everything else, and pressure begins building around the nerve that carries signal from each eye back to the brain. Month after month, that pressure transmits to the back of the eye itself. The rear surface of the eyeball flattens, slightly but measurably. The nerve swells visibly on a scan. A meaningful share of long-duration crew members come home seeing worse than when they left. Some need corrective lenses for the first time in their lives. Not a strained back, not tired legs. Something quieter and stranger than either. Your own eyesight, degrading from pressure building inside your own skull, with no outside cause at all. And on the next world, vision is never optional. Every task depends on it holding steady, reading a gauge inside a dim habitat, inspecting a seal before trusting it with a life, walking safely in a pressure suit with a helmet that already narrows the field of view, repairing hardware with thick gloves that need sharp eyes to guide them precisely, possibly someday treating an injured crewmate with nothing in reach but a medical kit, and whatever the eyes in the room can still resolve clearly enough to trust. None of that tolerates blur. And on a world where the nearest help is months away in every direction, there is no acceptable amount of degradation, only varying amounts of risk. There is a third front, and it happens to be the one science understands least. Several immune functions run differently in microgravity, not shut off, just dysregulated. working the wrong amount at the wrong moments. Viruses that already live dormant in most adult bodies, several members of the herpes family among them, begin reactivating and shedding more than they normally would. Nobody has fully mapped why yet. What is known is the pattern itself, and it has repeated consistently enough across enough missions and enough years that it is treated as an established fact of long-duration flight, even while the mechanism underneath it stays an open question. That is the honest state of the science. Not a gap glossed over, just named plainly. The first crews to make this crossing will be the ones characterizing that risk in real time for everyone who follows them. Put the whole picture together and it reads like this. Gravity is one more thing the homeworld hands a body for free, quietly, every second, without anyone noticing it is a gift at all. The crossing takes it away completely, and the only replacement anyone has built is 2 hours a day on a resistance machine, an engineered patch that slows the loss without ever fully stopping it. 6 to 9 months of that slow, patient disassembly runs the entire time beneath the calm, the silence, and the drifting stars. And it finishes its work at the exact moment it matters least to be finished. The crew that finally steps off that ship will carry thinner bones, smaller muscles, a reshaped heart, eyes already under pressure they did not have at launch, and a balance system that has to relearn, all at once, which way is down. They arrive at the hardest, most physically demanding stretch of the entire mission, already weakened by the stretch that came directly before it. And the body was never the only thing under quiet assault during those months. It was simply the one assault a crew could feel. The second assault does not announce itself the way the first one did. No soreness to notice, no ache to name, nothing a body can feel happening in real time. But the space between the two worlds was never actually empty. It is filled instead, continuously, with something moving fast enough and hitting hard enough to matter, and it never once lets up for the whole crossing. Two different things are doing the hitting, and they come from two different directions entirely. The first comes from the sun itself. The sun is not the calm, steady lamp it looks like from a porch on a summer evening. It spins unevenly, twisting its own magnetic field tighter over the years, then releases that twist all at once in brief, brilliant solar flares or in slower, days-long expulsions of plasma called coronal mass ejections. The most consequential of either kind fling protons outward at a meaningful fraction of the speed of light. These are solar energetic particle events, the sun at its most dangerous. Inside the homeworld's magnetic field, almost none of this reaches the ground. The field bends the protons away, and the little that gets through, the atmosphere soaks up. Out in open space, drifting between two worlds with no field and no air to hide behind, a crew receives them almost unfiltered. A major event striking an unshielded crew can bring on acute radiation sickness within hours. A very large one could kill. There is some warning. Solar observatories watch the sun continuously and can flag the early signs of a coming event. Tens of minutes to a few hours ahead. Sometimes more. Not days. Never days. So every serious mission plan for the crossing includes a dedicated shelter, usually a small inner chamber lined with water tanks, food stores, and whatever other dense cargo the ship already carries. On a warning, the crew retreats inside it and waits. The water and the food do double duty. They keep the crew alive, and at the same moment, they stand in the storm's way. That is the half of the problem a wall can solve. The other half cannot be walled off at all. Galactic cosmic rays arrive from far outside the solar system entirely. Atomic nuclei accelerate to nearly the speed of light by ancient supernovae. Most are simple protons. A meaningful share are heavier. The stripped nuclei of iron, silicon, calcium, elements forged and flung outward by stars that finished dying before the sun had even formed. They carry so much raw energy that they punch through almost any shielding a ship could plausibly carry. Worse, when one of them strikes the atoms in that shielding, it can shatter into a shower of secondary particles, neutrons, and fragments that go on to deliver a dose of their own. More shielding does not simply mean more safety. Not automatically. Add the wrong amount, and cosmic rays leave a crew worse off, not better. The home world's entire atmosphere is equivalent to about 10 meters of water sitting over every square meter of ground, stacked higher than a 3-story building. That is what it takes to meaningfully stop these particles. No spacecraft will ever carry that much mass. So for the whole crossing, every hour of every day, the crew absorbs cosmic radiation with nothing standing in the way at all. A small radiation detector riding one of the rovers already sent to the next world recorded exactly what that exposure looks like along this same route. The crossing alone approaches, and by some estimates matches, the career radiation limit historically set for astronauts in low orbit. A full mission, out, months on the surface, back again, would push well past it under nearly any plan proposed so far. The clearest consequence is a measurable rise in lifetime cancer risk. A newer, less discussed one concerns the mind. A heavy ion leaves a narrow, dense track as it passes, and where that track crosses a neuron, or the slender connection between two of them, the damage can resemble the cutting of a thread. Animals exposed to simulated versions of this in ground laboratories came away with measurable trouble navigating space, adapting to new rules, holding on to new memories. Whether human minds respond the same way is still an open question, one the first crews will answer simply by living through it. On the surface, at least, there is a real answer. Mass still works there, because a planet's worth of rock does not need to fly anywhere. Several meters of packed soil above a habitat cuts both kinds of radiation dramatically, and buried deep enough, the dose inside falls close to what a person absorbs, standing at sea level back home. The next world spent much of its early history erupting, and where old lava once flowed beneath a hardening crust and then drained away, it left long hollow tubes buried behind. Orbital radar has already found candidate openings, some wide enough to swallow a stadium, running for kilometers underground. A habitat built inside one would sit under meters of solid rock, insulated from the surface's temperature swings and shielded from radiation at once. Nobody yet knows whether any specific tube is intact, reachable, or safe. Finding out means a mission built specifically to look, and none has been planned. The mixture overhead is not constant either. The slowest, calmest part of it is the solar wind. A steady outward stream of protons and electrons moving at somewhere around 1.5 million miles an hour. Mild enough on its own that a shielded crew barely notices it passing. It is simply the baseline the more dangerous particles get measured against. Solar energetic particle events sit far above that baseline. Protons carrying hundreds of millions of times the energy of a single ordinary photon of light, arriving in bursts that last from hours to a few days. The largest, perhaps once per 11-year solar cycle, can spike thousands of times above background in a matter of minutes. Wait, that is backwards from what it should be. A quiet sun is not the safer time to fly. Solar activity runs on that same 11-year rhythm, cycling between busy stretches thick with flares and calmer troughs between them. It would seem to follow that a crossing timed for one of the calm troughs is the safer crossing. It is the opposite. The sun's own magnetic field, when active, pushes outward and deflects a share of the incoming galactic cosmic rays before they ever reach a ship. Let the sun go quiet, and that shield weakens too, letting more of the harder radiation through. A crew flying during a calm sun may end up absorbing a higher cumulative dose than one that flew straight through a busy one. There is no dose small enough to call harmless. Every bit of it simply adds to a running total, a small statistical weight added to a lifetime's odds. The first crews to make this crossing will accept that number knowingly, after being told exactly what it is. What they carry through it in bone density and eyesight, and now in radiation dose, will be measured and studied and used to write the numbers the next crew reads before they agree to go. Radiation does not end at the outer hull either. It is waiting on the ground too, in smaller doses but longer stretches. Before any of that though, there is the 7 minutes that decide whether the crew reaches the ground at all. Before there is anything else to survive on the ground, there is a stretch of time that will not wait for anyone. The crossing, for all its patience, ends in the one part of the whole journey that gives no time at all. The next world does have an atmosphere, thin as it is, and that thinness is exactly what makes arrival dangerous in two opposite ways at once. A spacecraft comes down out of the crossing at orbital speed, tens of thousands of kilometers an hour, and slamming into even a wisp of air at that speed compresses the gas ahead of the vehicle so violently that it ignites. The outer surface glows, scorches, and would burn straight through the hull without a heat shield absorbing and shedding that heat instead. But the same air that sets a descending craft on fire barely slows one down. It is thick enough to set things on fire, not thick enough to help much in slowing them. Surface pressure down at the ground comes out to less than 1% of what the homeworld carries at sea level, too little for the atmosphere to do the braking on its own. Every robotic mission that has ever landed there worked inside that limitation, and every one of them was light. A rover, a lander, a few hundred kilograms, occasionally closer to a metric ton. Parachutes and aerodynamic drag can lower a payload that size to a safe touchdown, and they have, again and again, mission after mission, a real and repeated engineering success. Each landing built confidence that the next one would work too, and each one did, quietly proving out the same basic recipe of heat shield, parachute, and a gentle final drop. Here's where it gets strange. That success does not scale. A crewed spacecraft is not the same kind of payload, not by a wide margin. It carries a pressurized habitat, life support for the entire surface stay, food, water, spare parts, medical supplies, scientific instruments, and the machinery needed to manufacture the propellant for the trip home. Add the crew themselves, sealed inside all of it, and the total mass climbs to somewhere between 20 and 40 metric tons, possibly more depending on the final architecture. No parachute system ever flown at this world has been tested anywhere near that scale. No lander built for it has come close. Landing lightly is a solved problem. Landing crew is not. The leading answer is propulsive descent. Instead of leaning on drag through the final phase, the spacecraft fires its own engines in the last stretch, using raw thrust to slow itself the rest of the way down to a controlled stop on the surface. The physics behind that is not in doubt. Rocket engines can absolutely produce enough force to slow tens of metric tons. The engineering is the open question. Doing it reliably, doing it autonomously, doing it in an atmosphere too thin to help, after 9 months of coasting has left every system untouched and unexercised. For a payload mass nobody has ever actually tried to land there. Every sensor, every valve, every line of guidance software has to wake up from months of silence and perform correctly on the very first attempt, because there is no dress rehearsal on this world with this much weight behind it. That gap has not been closed yet, and the first crews to attempt it will be finding out in real time whether it holds. The full sequence, from orbital speed at the top of the thin atmosphere to a stopped vehicle resting on rock, runs about 7 minutes start to finish. During those 7 minutes, there is no aborting, no calling home for a second opinion, no pausing to reconsider a choice already made. The radio signal announcing the entry has even begun takes long enough to cross the gap between the two worlds that by the time anyone back on the homeworld hears it, the whole sequence is already over, one way or another. Mission Control learns the outcome only after the outcome has already happened. That is why the people who build these systems call this stretch the 7 minutes of terror. Not for theatrics, not to make a quiet engineering problem sound like a thriller. It would seem to make sense that Mission Control, watching every prior landing on this world unfold live, is guiding this one too. It is not. The whole sequence finishes before the homeworld even learns it started. For those 7 minutes, the crew and the spacecraft's own automated systems are entirely alone with every decision being made. No hand on the homeworld can reach the controls. No voice can offer a correction mid-sequence. Whatever happens in that window happens without anyone outside the hall able to do a single thing about it. And it happens fast enough that by the time the truth arrives back home, it is already history. If every system performs the way it was built to, the ending is almost gentle. The engines cut out. The spacecraft settles onto chosen ground, dust and broken rock beneath it, and the structure begins to tick and cool in the sudden quiet. For the first time since leaving the homeworld, the crew hears something moving outside the hole that is not their own machinery. A soft hiss, thin and faint. Wind from an atmosphere barely there at all, brushing against the vehicle that just carried them across tens of millions of miles of empty dark. Months of silence, one committed sequence, and then this. Stillness of a different kind. A world instead of a void pressing gently against the hull. They have arrived. An arrival is not the end of the danger, only the start of a longer, quieter one, because almost everything waiting for them on the ground outside that hull is, in its own patient way, harder to survive than the crossing ever was. That soft hiss the crew hears through the hole is the first honest introduction to what is actually waiting outside. And the introduction turns out to be mostly a list of things that are simply not there. The surface is more hostile to an unprotected human body than almost anywhere the homeworld has ever let people build a permanent life. The hostility does not concentrate itself in one place or one hazard, and it does not wait for a storm or a season to arrive before it matters. It runs in several directions at once, present everywhere, at every hour, with almost nowhere to step out of its reach. None of it is dramatic by itself, all of it is lethal together. Start with the air, or the almost complete absence of it. Average surface pressure across the whole planet comes out to about 610 pascals, a measure of how hard the atmosphere pushes back against anything sitting inside it. That works out to roughly 0.6% of what a sea level afternoon carries at home. Thinner than the air at any altitude a commercial airliner is ever built to cruise at, and thinner by a wide margin. It would be tempting to treat that as a problem a mask could solve. Extra oxygen fed in over the nose and mouth against air too thin to breathe. It is not that simple. Physiologists have a name for the line below, which thin air stops being merely uncomfortable and starts being lethal in a very different way. It is called the Armstrong limit. Below it, water held inside the body's own soft tissue at ordinary body temperature begins to boil. Not from heat, from pressure, weight. There is no wound here, no puncture, no exposure to anything external at all beyond the air itself. The condition is called ebulism, and it needs nothing more than pressure too low to hold water as a liquid. Water inside soft tissue simply starts turning to vapor in place, because the surrounding pressure that normally holds it down has gone. An unprotected body on that surface would develop ebulism within seconds. Consciousness would follow within 10 to 15. Whatever the word survivable is supposed to mean, it does not mean this. A number measured in single-digit seconds is not a margin. It is barely a warning, not a mask, a full portable atmosphere. That is what a suit actually is out there. Not an accessory, but the entire difference between a body that lives and a body that does not, every single time a boot crosses the airlock threshold. It is a sealed bubble of held pressure and breathable air wrapped around one person, the thinnest possible barrier between a human body and a place where that body cannot exist unprotected for more than a few seconds. And pressure is only half the problem. Even sealed at the right pressure, the air just beyond the suet would not sustain a single breath at any pressure at all. The atmosphere out there runs roughly 95% carbon dioxide, with small measures of nitrogen and argon making up most of what remains, and only a trace of oxygen buried somewhere inside that mixture. There is, for practical purposes, no breathable air anywhere on the surface, not in a lungful, not anywhere. Every breath a crew draws for the length of an entire stay has to be produced from local resources by equipment that is not allowed to fail or carried from the homeworld at a cost that makes every liter of it precious. Step outside the habitat's walls in any direction for any reason, and that fact does not change. There is no ridge to walk over into thicker air, no valley low enough to breathe in unassisted. The whole planet keeps the same arithmetic. Then there is the cold, and the cold does not wait for the pressure problem to finish first. Surface temperatures range from roughly 143 degrees below zero at the winter poles, cold enough that carbon dioxide freezes directly out of the thin air and settles onto the ground as a kind of seasonal dry ice snow, up to perhaps 20 degrees above zero on the warmest equatorial afternoons. It would be easy to picture that as a harsh winter and nothing more. Not a harsh winter. Nothing on the homeworld compares. Frozen air, falling as snow. Cold enough to end a life in minutes. The average surface temperature runs close to 60 degrees below zero. Colder than any place on the homeworld where a person has ever lived without active life support holding the line for them. A severe homeworld blizzard rarely drops much past 30 below, and even that is treated as an emergency. Warnings issued, travel halted, people told to stay indoors. An ordinary day out there starts twice that cold, and some days get worse with no season in which it lets up for long. The thin atmosphere holds almost no heat of its own, so the ground warms fast at sunrise and loses it just as fast at sunset. The swing between a single day and the following night can run 60 to 70 degrees, a larger daily temperature swing than anywhere the homeworld has to offer. A suit does not just have to hold air and pressure against the body wearing it. It has to hold a survivable pocket of warmth across that entire range, every day, for years, without a single failure. Pressure, breathable air, a stable temperature. At home, all three arrive without being asked for. Quietly, continuously, built into the air itself, since before anyone alive was born into it. Nobody manufactures the pressure in a homeworld afternoon. Nobody builds the oxygen into a homeworld breath. Nobody engineers a homeworld morning to stay above freezing. Out here, none of it is given. All three have to be manufactured, carried, sealed, and actively defended, hour after hour, for as long as anyone intends to stay. Or the difference shows up almost immediately, and it shows up as a body that cannot survive the next few minutes. That is the arithmetic sitting underneath every suit, every airlock cycle, every hour spent outside a shielded hull. It is not a hazard that can be solved once and then set aside. It has to be solved again every single day, by systems that are permitted to fail exactly 0 times. Pressure, air, and warmth turn out to be only the first 3 entries on a much longer list, and the surface does not wait for anyone to finish reading it before presenting the rest. Radiation does not wait for the door to open before it starts working on a body either. The next world has no global magnetic field left, and only a sliver of atmosphere above it. The 2 things that keep high-energy particles off a body at home. Without them, the dose reaching the ground runs many times higher than anywhere on the homeworld surface. It is not, however, as bad as the crossing. The thin air overhead still filters a little of it, and the planet itself blocks half the sky at any given moment, absorbing whatever tries to arrive from below. So a body standing on the ground is only ever exposed to half the sources a body drifting in open space would face. A crew member standing on the surface takes in a meaningfully smaller daily dose than the same crew took in drifting through open space to get there. Meaningfully smaller is not the same as safe. A long stay still calls for meters of shielding overhead, underground, or under a covering of packed soil, or inside one of the tubes carved out by ancient lava flows, the same mass this catalogue already spent time on. Absent that kind of mass, the schedule itself becomes the shield, most of every day spent inside the covered habitat, only carefully rationed stretches spent outside it. The exposure budgeted and tracked the way a homeworld household might track spending against a fixed monthly limit. The ground under that habitat looks, at a glance, like something you could plant in. It is not. Not soil. Poison. Dressed as soil. The next world's dust and rock carry perchlorates at concentrations the homeworld simply does not produce. Simple, reactive chlorine compounds that jam the thyroid gland's ability to take up iodine. The hormone system's control knob for metabolism. In any real quantity inside a human body, they are toxic. At their natural concentration in the ground, they are potent enough to kill most candidate crops outright. So a handful of ordinary garden soil, harmless anywhere on the homeworld, becomes something a crew has to treat and clear before it can touch a living plant or a living lung. So the moment dust rides in on a boot or a glove, it is not housekeeping, it is a contamination event. Airlocks earn their keep managing that dust as much as they manage pressure, brushing and vacuuming the outside of every suit before anyone opens the inner hatch. Growing anything in the local ground means stripping the perchlorates out first, an energy-hungry chemical process, or diluting them with enough imported organic material to blunt them, or skipping the ground entirely and growing in something that never touches it. Every one of those 3 choices costs time, energy, or both. And none of them is optional if the crew intends to eat anything grown rather than only what arrived with them. The dust causing all that trouble is almost impossibly fine, smaller than a single grain of pollen, and it carries its own static charge. With no rain anywhere to rinse it off, it clings to whatever it touches and stays there. It works into hinges and joints, settles across solar panels, seeps past airlock seals, coats camera lenses and suit seams, and every exposed connector. Equipment that runs flawlessly in a clean lab back home can fail in ways nobody anticipated, after months of that same fine, charged, chemically hostile dust working its way in. Sometimes the dust stops being a nuisance and becomes an emergency. Regional storms are common, and occasionally the whole planet is swallowed at once, a storm lasting weeks and sometimes months, during which the sunlight reaching the ground drops to a fraction of what it was. The sky itself turning the color of dim rust for as long as the storm holds. One solar-powered rover ran for almost 15 years, far longer than anyone who built it expected, before a planet-wide storm finally silenced it, draining its batteries faster than the dimmed sun could refill them. It simply went quiet and stayed quiet, A crude habitat cannot afford that kind of silence. Life support does not get to pause for the weather, and a battery that empties during a months-long storm empties for every system depending on it at once. Air scrubbers, heaters, water processing, all of it together. It would be easy to picture those storms as violent, wind tearing at a habitat wall. The thin air makes that picture wrong. A storm wind moving 100 kilometers an hour out there pushes with roughly the force of a gentle 10 kilometer an hour breeze back home. It will not tip over a structure. It will not knock a person off their feet. What it moves is dust, lifted, carried, and left to settle into every gap left uncovered. Then, there is the light itself. The next world has nothing like the homeworld's ozone layer. No high shield of oxygen molecules absorbing ultraviolet before it reaches anything below. Every material exposed to open sky, plastics, seals, coatings, the polymers holding suits and instruments together, degrades under it far faster than anything rated for homeworld sun. Left unprotected, gear that should last for years can weaken within months. All of that is simply what is waiting outside on an ordinary day, before a single boot leaves the airlock. Getting ready starts hours ahead of the walk itself. You check the radiation forecast, check that the airlock cycles cleanly, check that the suit has been serviced and sealed since its last use. You climb into it slowly, layer by layer, pressure garment, insulation, the hard shell carrying its own air and heat, and carbon dioxide scrubbing, because a seal, fastened carelessly, becomes a leak with nothing outside to help you fix it. The helmet locks. The suit takes over breathing for you. You are, from that moment, a small spacecraft shaped like a person. The outer hatch opens onto dust and thin pink light, and boots leave prints in ground that has sat undisturbed for billions of years. Every step costs more than it would at home. Stiff joints resisting each motion, gloves turning simple tasks into slow, deliberate ones. A gloved hand that could tie a shoelace at home might need 3 tries to turn a small bolt out there. 4 hours pass, sometimes 6, running instruments, repairing what needs repairing, before the walk back to the airlock. The cycle through, the careful brushing away of whatever perchlorate dust made it this far. Tomorrow asks for the same routine. So does the day after that. For months, then years. No stepping outside without the suit. No open window. No smell of rain or grass or anything alive. The world out there is strange and beautiful in its own right. And it is also, patiently, always trying to end the life inside that suit. And every one of those hours, suited or not, happens without another human voice, close enough to answer back in real time. The walls that keep the surface out do nothing about a second kind of distance, one that follows the crew inside the habitat and never lifts for the whole length of the stay. It is not measured in dust or cold. It is measured in minutes, the time a radio signal needs to cross the gap between the next world and the home world, even moving at the speed of light. No engineering choice made on either world can shorten that trip for a signal already committed to it. That gap is never fixed. The 2 planets swing around the sun on different paths at different speeds, so the distance between them is always changing, and the delay changes with it. At closest approach, a signal takes about 3 minutes to arrive. When the worlds sit on opposite sides of the sun, the same signal takes closer to 22 minutes to make the same crossing. A full exchange, a question sent and its answer received, runs anywhere from 6 to 44 minutes, depending on where the 2 worlds happen to be that day. Ask a single question near the long end of that range, and the answer does not arrive until you have cooked a full meal, eaten it, and started cleaning up. The better part of an hour spent waiting on one sentence to cross the dark. There is no real-time conversation across a gap like that. Not a phone call, not a chat window, filling in as someone types. Every exchange with anyone outside the small group in the habitat becomes a message sent into the silence, answered minutes later, then answered again minutes after that. A conversation stretched so thin it barely resembles one. It would be easy to assume Mission Control talks a crew through whatever goes wrong. But here's where that assumption falls apart. The descent onto the surface already showed what the delay looks like at its sharpest. A sequence that starts and finishes before the homeworld even learns it has begun. The same rule holds for every emergency that follows landing. A leak in the habitat's pressure seal has to be found and stopped by the people breathing that air in the minutes they actually have. A fire has to be fought by whoever is standing closest to it. A medical crisis gets whatever expertise happens to already be in the room, nothing more. A suit failure on a walk gets solved by the person wearing it, with the rest of the crew helping from just outside. Ground control can be told what happened and ask for advice, not talk through it, live through it, alone, and only report it afterward. This is not a gap better engineering closes. It is set by the distance and the speed of light, and no amount of money or cleverness changes either number. So every system that keeps the crew alive has to be understood by at least one person in the habitat, ideally more than one, deeply enough to diagnose a failure and repair it under pressure, in the field, sometimes inside a pressure suit, with only the tools and spare parts that came along on the crossing. Training for a mission like this does not stop at teaching one person to fly the ship and another to keep the water clean. It spreads that knowledge as wide as it can across the crew, because counting on any single specialist to stay healthy, rested, and available for years with no backup is not a plan. It is a hope. No previous crewed mission has ever asked this much independence of the people flying it. None of this is treated as a failure waiting to happen. It is simply the operating condition of the mission, understood and trained for long before launch, in the same spirit that a mountaineering team prepares for a stretch of a climb, where rescue is not an option. Not because rescue is unlikely to be needed, but because it will not be there if it is. The same silence reaches into smaller things too. A message home is not a conversation, it is a recording, sent out and received minutes later by someone who then records a reply and sends it back across the same stretch of empty space. Parents, partners, old friends, the people running the mission from the ground, all of it takes the shape for the entire length of the stay. A birthday, an anniversary, a piece of news from home, all of it arrives the same way, minutes late, one direction at a time. Crews learn to write longer, fuller messages, since there is no chance to clarify a misunderstanding in the moment, only in the next long exchange, a day or more away. The interruption and response ordinary talk depends on. The part where one voice catches another mid-sentence and the thought changes course together, simply does not exist out there. The crew watches the distance grow in both directions. Behind them, the homeworld shrinks to a single bright point in a dark sky. Ahead of them, the next world grows from a reddish speck into a disk, and finally into a landscape they can walk on. Every person they have ever loved lives on that one small point of light, reachable only through a delay longer than any human relationship has ever been asked to carry. It is not an unbearable distance. People have survived longer separations, on long expeditions, and in long wars. But this one never breaks. Not for a single hour of a multi-year mission. And it never takes a day off. There is something almost steadying in that, once its shape is understood. The distance does not change with how anyone feels about it. And it does not negotiate. It simply is. Every hour. For as long as the mission runs. Whatever it costs the crew in company, it costs the same in rescue. Out there, the only responders they will ever have are each other. And that was only the first thing the distance would ask of them. Being your own emergency room is only the first form of independence the distance demands. The crew must also become their own supply chain, because nothing that matters can be shipped to them in time to help. Everything they have, they brought. The next launch window will not open for another 26 months. The same slow clock that decided when they could leave the homeworld in the first place, and the same clock that will decide when they can come home. A resupply ship sent the moment they touched down would still not arrive for the better part of a year. By the time it landed, whatever problem it was meant to solve would already be over, handled with what was on hand, or not handled at all. There is no expediting it. There is no second option waiting in reserve on a faster track. There is only what already left the ground and what the crew can make for themselves once they get there. A single person needs roughly 2 pounds of food a day, roughly 2 pounds of oxygen a day, and several gallons of water a day for drinking, cooking, washing, and the ordinary maintenance of a working body. None of those numbers sounds like much on its own. Multiply the first one by a crew of 4 and by a 500-day surface stay, and the food alone runs past £16,000, more than 4 loaded family cars stacked one on top of another, just to keep 4 people fed until the return window opens. Add the oxygen and the water stacked on top of that, and the total mass no longer fits inside any spacecraft yet designed to carry it, let alone one that also has to carry the crew, their habitat, and their tools. It would be easy to picture a colony resupplied the way a remote research outpost gets resupplied. A truck or a ship arriving on a fixed schedule whenever the pantry runs low. Not here. Not on this clock. The next delivery is up to 2 years and a year's transit away, decided by orbital mechanics rather than by anyone's need, and a plan built around waiting for it is not a colony at all. It is a string of expensive visits that happen to touch the ground and then leave again. So almost everything long-term must be produced locally instead, pulled out of the ground and the air by machines the crew carries with them and keeps running themselves for years without a repair shop to fall back on. The formal name for this is in situ resource utilization, using what a place already has rather than hauling in what it lacks. It is not a convenience added for efficiency, the way better insulation or a lighter alloy might be. It is the one thing standing between a handful of short, expensive expeditions and an actual foothold that lasts. The difference between visiting and staying. The raw materials are, in principle, already there. First, the atmosphere is almost entirely carbon dioxide, and carbon dioxide is the feedstock for a well-understood chemical process that combines it with hydrogen to produce methane and water vapor. Second, the methane becomes rocket propellant, well matched to the next generation of engines already being built for the trip home. So the fuel for leaving does not have to be carried in on the way there. Third, the water vapor is captured and split by an electric current into hydrogen and oxygen. The hydrogen fed back into the reactor to make more methane, the oxygen breathable. Run patiently enough, the same small loop makes fuel and air out of nothing but sunlight, electricity, and a thin, poisonous sky. One of the recent rovers carried a small instrument built to test exactly this idea, pulling oxygen straight out of the thin carbon dioxide air using electricity alone. Over more than a year of runs, spanning different seasons and different times of day, it worked, producing oxygen at a rate of roughly 6 to 10 grams an hour. A crew of 4, breathing continuously, needs roughly 1 kilogram of oxygen every hour. Not close, not in the same range. A working demonstration and an operational life support system are separated by a factor of roughly 100, and closing that gap reliably for years, unattended, in cold and blowing dust, is the harder half of the problem, harder than the chemistry itself. The chemistry is proven. The scale is not, and no one yet knows exactly how long closing it will take. That chemistry also needs a steady supply of hydrogen, and the thin air overhead does not hold much of it. The likeliest source is buried instead, water ice mixed into the soil at sites well away from the equator, mapped from orbit by radar that reaches beneath the surface and by instruments that sense hydrogen directly in the ground across a wide range of latitudes. Knowing the ice is there is not the same as having it. Reaching it means drilling or digging down, hauling the ice up, melting it, and running a current through it. Each step its own machine, its own maintenance schedule, its own quiet way to fail in the cold and dark of a winter, far from any supplier of spare parts. Food carries a version of the same problem. The ground itself is not a garden waiting to be planted. It lacks the organic matter and the microbial life healthy soil depends on, and it carries the same soil poison already met on the surface walks outside, the compound that disrupts the thyroid and kills most crops at natural strength. Growing anything in it means one of three slow paths: stripping that poison out first through an energy-hungry chemical process, working the soil for years until enough of it is diluted and a living microbial community can take hold, or skipping soil altogether and growing roots suspended in water or a fine nutrient mist instead. A method already proven at home and already tested in orbit that sidesteps the poison ground entirely. Even soil-free growing needs light, and the sun here gives less than half of what it gives at home. A habitat buried under meters of soil for radiation shielding sees no direct sunlight at all. So every plant grown indoors grows under lamps instead, and those lamps draw from the same finite supply of electricity that keeps the air breathable, the water flowing, and the habitat warm through nights that fall far below freezing. None of these systems, the oxygen reactor, the ice mining rig, the hydroponic racks under their lamps, is finished technology today. Each is proven in principle and unproven at the scale and duration a real colony would demand, and the first crews to rely on them will be finding out, in practice, which methods actually hold up. Oxygen, water, propellant, food, all of it traces back in the end to one source, the current running quietly beneath every other system on the base. That current turns out to have its own kind of brutality. Follow that current back far enough, and it runs underneath everything already named. Life support runs on it. The reactor pulling oxygen from thin carbon dioxide air runs on it. The pumps hauling buried ice out of the cold ground. The current splitting the ice into hydrogen and breathable oxygen. The lamps standing in for a sun that never quite arrives. The heaters holding a habitat above a night that falls far below freezing. All of it draws from the same wire. Power is not one item on a long list of survival systems. It is the layer underneath the whole list. The one thing every other system quietly assumes will keep flowing. Every survival system built into the habitat is, underneath its own particular engineering, an electrical appliance first. The oxygen reactor is an electrical appliance. The ice miner is an electrical appliance. The grow lights are an electrical appliance, and so is the heater standing between a sleeping crew and a temperature that would kill them within hours. Fail the power, even briefly, and it is not one problem that appears. It is every problem at once, in every system, simultaneously. Take it away for long enough, and every other system, however carefully designed, however well tested, simply stops. That makes the choice of power source one of the most consequential decisions a base ever makes, and the obvious answer looks obvious for a reason. A red desert under a bright sky reads, at a glance, like a solar planet. Sunlight for free, no fuel to haul across millions of miles, no moving parts to wear out or fail. Every robotic mission that has ever worked the surface has run on exactly that logic. Panels unfolding in the thin light and quietly charging batteries for years at a time. It is a clean, simple, appealing picture, And for a machine that only needs to think and roll and photograph, it has worked well enough for years on end. But here's the problem the panels quietly carry with them. The next world sits farther from the sun than home does, and a panel here collects only about 40% of what the same panel would collect back there, before a single grain of dust ever settles on it. And dust does settle, constantly, charged by static, never rinsed away by rain, thickening on the glass week after week, with nothing to interrupt it. Then the storms arrive on top of that steady loss. A regional or global dust storm can dim the sky for weeks, sometimes months, cutting the sunlight reaching the surface to a fraction of what a panel needs to keep pace with demand. One long-running solar rover already learned this the hard way. Its batteries finally drained past recovery when a planet-wide storm blotted out the sky for good, ending a mission that had otherwise run for years past anyone's expectation. A robotic rover can afford to wait out a storm in low-power sleep and wake when the sky finally clears weeks or months later. A crewed base cannot. Life support does not pause. Oxygen production does not pause. Heating a habitat through a freezing night does not pause for anyone's convenience, storm or no storm. Not a backup source. The primary one. That is what the mission actually needs, and free sunlight, however appealing, cannot promise it. So the honest engineering answer turns out to be nuclear, not solar. A compact fission reactor does not care whether the sky is clear or choked with dust, whether it is midday or the dead of a polar winter. Its output depends on one thing only: fuel loaded and the machinery running, indifferent to weather in a way no panel will ever be. A small space-rated reactor design has already proven the core idea works. Tested on the ground back home at a modest output, somewhere around 10 kilowatts, enough to run perhaps 8 or 9 ordinary homes at once. A crewed base would need hundreds of kilowatts, the steady draw of a small neighborhood, not a handful of houses. A growing colony would need megawatts, the draw of a small town. Between a working 10 kilowatt prototype and a reactor built to survive an interplanetary crossing and then run unattended for years at that far larger scale sits a substantial engineering program, still very much underway. And the reactor is only half the problem. Any machine that splits atoms for a living leaves home under a different kind of scrutiny than a fuel tank or a solar panel. Regulatory approvals, safety protocols, launch safety reviews, checking what happens if a rocket carrying it fails on the way up. All of it has to be cleared before a single reactor reaches a launch pad, layered on top of the engineering itself. The honest picture, put plainly, is a path that is real but not finished. The physics is settled. The scale is not, and no one yet knows exactly how long closing that gap will take. This is not a crash program chasing a deadline. It is patient work, carried forward on the same decades-long timeline as everything else quietly being solved before anyone boards a spacecraft, by engineers who will hand the unfinished parts of it to whoever comes after them. The wiring, in other words, is a hard problem with a known shape. Engineers can already see the path from here to there, even if no one has walked the whole of it yet, and every year of ground testing narrows the distance left to cover. What waits at the far end of the transit, the landing, and the long surface routine is a different kind of problem entirely. Inside the small group of people actually living inside all this careful engineering, warmed and lit and kept breathing by a current no one out there can see, there is no wiring diagram at all. The machines all trace back to that same current, and every one of them, however delicate, can in principle be diagrammed, tested, repaired by someone who understands its wiring. The people who keep those machines running cannot be repaired the same way, and what holds them together across years of sealed, distant life has no equivalent blueprint at all. Some of the hardest problems on a mission like this are not mechanical or chemical or orbital. They live inside the heads of the people who fly, and they are documented well enough by decades of research on smaller, gentler versions of the same condition to count as serious operational concerns, not vague worry. A crew would spend years inside enclosed quarters with the same small group of people, unable to step outside without first sealing themselves into a suit, unable to feel any part of the natural world their bodies evolved inside. No open air, no rain, no birdsong, nothing alive beyond themselves and whatever they managed to grow under a lamp. Every message from anyone outside that small group arrives minutes late, and every day looks enough like the day before it that the calendar starts to feel optional. Researchers already know roughly what that does to a person, because smaller versions of it have been studied for decades. Small teams that winter over at high-latitude research stations, cut off from aircraft for roughly 9 months at a stretch, consistently show measurable cognitive change by the end of the season. Processing speed slows, spatial reasoning gets worse, mood becomes harder to regulate. Submarine crews show it, long polar expeditions show it, remote oil platforms show it. Volunteers in sealed simulation habitats show it too, and researchers have pushed the comparison further, sealing crews into isolated domes on the slope of a volcano for stretches of up to a year, while a separate program on the other side of the world locked a crew of 6 inside a habitat for more than 500 days, simulating an entire round trip, communication delay included. Both documented the same pattern: interpersonal friction, falling motivation, slower thinking. And every one of those volunteers knew the whole time that they were still on the home world, that the door could be opened, that rescue was one phone call away. A real crew gets none of that. Smaller crew, smaller habitat, no evacuation of any kind, and the constant background knowledge that a missed suit check or a misread gauge could end everything for everyone in the room. Some of what the crew loses cannot be measured on any cognitive test at all. Years pass without wind moving across skin, without the smell of rain, without leaves stirring in a breeze, without a horizon that is not also a geology lesson. The world outside the viewport runs reddish and grey in every direction. Sound arrives, muffled through thin air and a suit visor. And the homeworld, when they can find it at all, is a small bright point in the sky, barely distinguishable from any star nearby. That absence cannot be fixed with better engineering. It can only be lived inside. It would be easy to picture that as unbearable, some daily crisis of nerve playing out behind the visor. It is not that. The real brutality of the isolation is quieter than that, and, in its own way, harder to fight. Not a crisis, a condition. It sits in the background of every single hour of every day of a mission that runs 2.5 to 3 years, never sharp enough to name as an emergency and never absent either. The steady hum underneath everything else the crew is doing. Here's where the assumption most people carry gets it backward. It seems obvious that the biggest risk to a mission like this is technical. A valve, a seal, a circuit board. That is not the safest assumption. A mission can fail for a human reason instead. One person's judgment or temper or exhaustion cascading through a crew with nowhere to walk it off. That risk is why crew selection has become one of the most demanding filters ever built for any job. Technical skill and physical fitness matter, but they are the easy part. What matters more is a specific, quieter kind of resilience, not the absence of frustration or grief, but the capacity to carry it without letting it spill onto anyone else. Studies of people who thrive in long confinement point away from the dramatic. Not bravery under fire, persistence through boredom. The ones who do best are the ones who keep brushing their teeth on schedule, keep showing up curious and useful, at month 11, in a room they have already memorized down to the last rivet. Some of that is trained. Some of it may simply be who a person already is. And reliably telling the two apart in advance remains one of the least understood problems in the whole program. Choose wrong, and the most expensive expedition in history can fail for a reason no engineer could have caught. What actually keeps a small crew whole across that kind of pressure is unglamorous. A schedule for work, meals, exercise, sleep, quiet time, crew meetings, and private check-ins with a psychologist on the other end of a long delay. Small, deliberate traditions. A birthday marked, an anniversary remembered. The same small rituals every isolated group in history has invented for itself. Friction still happens. It would be strange if it did not. 6 or 8 people sealed together for years, grating on each other in ordinary human ways. The discipline is not pretending that friction away. It is catching the small rupture early and mending it before it grows into something the crew cannot recover from. And holding that discipline usually falls hardest on whoever the crew looks to, as its physician, its psychologist, or its quiet leader, though in practice, every member carries some share of it. It is not a skill taught anywhere else on the homeworld, because almost nothing else asks for it at this intensity, and it is being learned slowly, mission by mission, aboard the orbital station and inside the analog programs. One lesson at a time, long before any of it gets used for real. The habitat is seeded, on purpose, with pieces of the world they left. Plants growing green under artificial light, old photographs, music recorded long before launch, messages saved and replayed until the edges of them are soft. None of it solves the isolation. All of it is the slow, patient work of keeping a household of a few people functional and whole, in a place with no rescue if that work quietly fails. For 2.5 to 3 years, longer than the run of many university degrees, start to finish. The machines have a wire that runs back to a reactor or a panel, and it can be traced end to end by anyone willing to follow it. What holds the crew's minds together has to be built the same patient way. One habit and one repaired friendship at a time, with no test bench and no manual anywhere for it. That discipline can carry a mind through years of sameness. It has no answer at all for what happens when it is the body, not the mind, that breaks. The absence of rescue is not only a weight carried in the mind, it is also a hard limit on the body, and it is a limit the crew has to accept before they ever leave the ground. There is no ambulance on the next world. There is no hospital to divert toward, no specialist to page from a hallway, no team waiting scrubbed in on the other end of a phone call, no siren, no stretcher crew arriving in minutes. Whatever happens, happens inside the same sealed rooms the crew already lives in, with the same small group of people who happen to be on shift when it starts. The same distance that turns every birthday message and every piece of news from home into a delayed recording also turns every medical emergency into something the crew alone must resolve, start to finish, without a second opinion arriving in time to matter. Whatever guidance they can pull through, that lag arrives late, sometimes badly late, and by the time an answer comes back, the situation on the ground has often already moved past the question that prompted it. There is no pausing the emergency to wait for a reply. Training, an onboard kit, and whatever delayed advice eventually makes it through the silence are not a supplement to real medical care out there. They are the entire medical system, complete and final, the moment something goes wrong. Here is the honest implication most people never sit with. Some conditions treated as routine at any homeworld hospital would not be survivable on the early next world. A burst appendix, at home, is handled so often and so reliably that most people barely register it as dangerous. A surgeon opens, removes, closes, and the patient is walking within days, one of the most unremarkable emergencies in modern medicine. On the surface of the next world, that same burst appendix becomes an entirely different event. Whichever crew member carries the most training in abdominal procedures has to open another human being in partial gravity inside a sealed habitat, working from a checklist and a kit instead of a fully staffed operating room, with no possibility of pausing the attempt partway through and no possibility of calling for a more experienced pair of hands. There is no faster ship waiting outside. There is no backup surgeon on standby. There is only the crew already there, not a failure of equipment, a property of distance and time. Mission planners do not pretend otherwise. They build the most complete medical kit the available mass and volume can carry. They train the crew as thoroughly as the schedule allows. They add redundancy wherever redundancy is physically possible, a second person cross-trained on every critical procedure, spare instruments packed against the failure of the first set, backup supplies of anything that might be consumed in a single crisis, and never replaced until the next resupply arrives years later. None of that is done casually. It is the product of long, careful review by people who have spent entire careers trying to close this exact gap as far as it can be closed. And then, plainly, openly, in the mission planning documents themselves, they accept that a category of the medical event exists for which there will be no satisfactory answer, regardless of how well the kit is stocked, or how many hours of training a crew member has logged before launch. That gap is not a design flaw waiting on a smarter engineer to close it. It is simply what distance costs, and no amount of additional hardware fully buys it back. So the first crews will not travel the way earlier crews traveled. At least one member will carry medical training that goes far past ordinary first aid, ideally surgical training, critical care skills, and the judgment to read a diagnosis from a limited instruments under pressure, without a radiologist or a lab a floor away to confirm the read. They will have access to automated diagnostic tools and remote surgical guidance systems, technologies still being built and tested right now, designed to stretch a distant specialist's expertise across months of communication lag, letting a surgeon on the home world talk a crew member through a procedure hours after the crisis actually began. And even with all of that in place, the realistic ceiling of care inside an early habitat sits below what a modern hospital delivers as a matter of routine. It will stay below that ceiling for years, not because anyone stopped trying to raise it, but because raising it any further runs straight into the same wall of distance that shapes everything else out there. The first crews will know this before they ever climb aboard, and they will go anyway, because what they are attempting is worth the risk to them personally. Part of what makes a person suited to a mission like this is not physical toughness or technical brilliance, though both help. It is a specific, practical calm. The ability to look directly at a serious medical situation, recognize it honestly for what it is, and do the best that is actually possible with what is on hand, without panic, and without giving up on the person in front of them. No dramatics, no false reassurance, no pretending the ceiling is higher than it is, just steady hands doing what steady hands can do inside a limit that engineering alone cannot lift. It is the same quiet resilience that carries a crew through years of sameness, aimed now at a single body instead of a shared state of mind, tested in an afternoon instead of stretched across a mission. That same quiet acceptance of a hard, honest ceiling runs through nearly every layer of a mission like this. It shapes the kit, the training, the crew roster itself, and it surfaces again, just as plainly, in a question that has nothing to do with medicine at all. The question of when a landed crew is even allowed to leave. Distance decides more than whether help can arrive in time. Long before liftoff, it also decides when anyone is allowed to leave the surface at all. The same orbital geometry that shapes the outbound crossing does not loosen its grip once the crew has landed. The two planets keep moving, each along its own path at its own speed, and the distance between them keeps changing every day, whether anyone on the ground is paying attention or not. A return trajectory that does not demand an impossible amount of fuel exists only once inside that familiar 26-month cycle. The same rhythm that decided when the crew could leave home in the first place. A crew who lands finds the window for leaving locked to that same clock, running on schedule far above their heads, indifferent to how the surface stay is going. In the most carefully studied plans, that means a wait of approximately 500 days on the surface before the geometry allows a safe trip home. Land just before the window opens, and the wait runs shorter. Land just after it closes, and the wait runs longer. Either way, the number is not adjustable. 500 days lands close to twice the length of an ordinary human pregnancy. A couple of months short of 2 full terms laid end to end, and every one of those days happens on a world that offers no early exit. Not a planning choice, a consequence of the planets themselves. There is no shortened mission, no calling it off early because the crew is tired, or homesick, or simply ready to leave. An emergency departure remains possible only in its most degraded form. A desperate dash that would land the crew back home in worse condition than if they had simply waited the window out. So they wait, and the waiting is not empty time. Across those 500 days, the crew runs the mission, maintains the systems keeping them alive, eats what their own equipment grows or what they carry down with them, breathes air their own reactors made, and tests every piece of life support against the slow accumulated weight of ordinary use rather than a short demonstration. 500 days is long enough to learn what actually works on a world no engineer back home can walk out to and inspect. Long enough to run the real science the mission was funded to do. Calibrate the systems that make air, water, and fuel out of local ground, and quietly stress. Test every piece of hardware the way a short visit never could. It is also long enough to leave something solid behind, tested and proven, for whichever crew comes next. Then the wait ends, and a different kind of pressure begins. The ascent vehicle, the small rocket that will lift the crew off the surface and back into orbit, has spent that entire year and a half sitting outside doing nothing but enduring. Dust settles on it season after season. Cold and thin sunlight bake its surfaces through wide daily swings, over and over, thousands of cycles before anyone climbs aboard. Ultraviolet light, strong enough to degrade seals and coatings built for far gentler places, falls on it every clear day with nothing overhead to soften it. None of that stopped it from having to work. It must fire, and it must work the first time. There is no service bay to tow it into. No backup rocket idling nearby. No second attempt if the engines fail to light. So why not just send the crew down first, and work out the ride home after they land? Here's the logic every serious plan refuses to skip. The ascent vehicle is not built on site once the crew arrives. It is sent years ahead of them, alone, aboard an earlier uncrewed mission, and left sealed on the surface to wait. Its propellant is not carried from home either. It is manufactured after landing, from the same chemistry the rest of the surface systems already lean on. Carbon dioxide pulled from the thin air combined with hydrogen drawn from buried ice, run through a reactor that builds fuel and breathable oxygen out of a world that started with neither. By the time a crew is cleared to leave home at all, that tank should already be full. Cleared to leave, not simply scheduled to leave. Mission planners confirm the propellant plant worked correctly for the months it takes to fill the tanks. They confirm the ascent vehicle is healthy. They confirm every system will function on the one day it is asked to. None of that confirmation happens by a technician walking out and looking at the hardware. There is no technician there yet, only sensors reporting home across the same long delay every other signal travels. Pressure readings, tank levels, engine diagnostics, arriving minutes late and trusted anyway because they are the only evidence anyone has. Only once that distant evidence adds up does a crew receive permission to begin their own crossing, because no serious architecture sends a person on a one-way trip before the trip home is already sitting there, verified, waiting. Send the hardware first, prove it works, only then send the people. The catch never fully disappears. Every piece of that pre-deployed hardware still has to survive its own crossing, its own entry and landing, and years of unattended operation on a world with no repair crew standing by. When the ascent vehicle finally does lift the crew clear of the surface, they meet the larger return ship that has been waiting quietly in orbit since the day they landed, and climb aboard for a second-long crossing, 6 to 9 months this time. The same slow disassembly that took hold on the way out takes hold again on the way back. Bones that had only begun rebuilding under a third of a gravity thinning once more. Muscle that regained some strength during the surface stay shrinking again. The same upward drift of fluid pressing again on the same optic nerve. The invisible fire between the worlds is still there too, and it does not care that this crew has already absorbed a full crossing's worth of it. The dose keeps adding to what the body carried out and never fully spent. Behind them, the world they are leaving shrinks to a rust-colored point. Ahead of them, slowly, the homeworld grows from a bright blue speck into a disk, and finally, unmistakably, into a place again. Add up the outbound crossing, the 500 days of waiting, and the return, and the whole arc runs close to 2.5 to 3 years. One continuous commitment stretching across a meaningful fraction of a working life, planned down to the month before the crew ever leaves the ground the first time. Not a season away, not even a year. A stretch of life measured the way careers are measured, and nearly all of it spent trusting hardware no one back home can walk out and touch. None of it happens without the 2 pieces of hardware the crew has trusted with everything the whole time. The suit that lets them stand outside at all, and the habitat that has to hold together around them for every one of those days on the ground. 2 objects will hold the entire 2.5 to 3 year arc together, and right now, neither one exists in the form the mission actually needs. Start with the suit. Every time a crew member crosses the airlock, they are not putting on clothing. They are stepping into a wearable spacecraft, a sealed pressure vessel built around a human body, and it has to do several difficult things at once. It must hold internal pressure high enough to keep its wearer alive against the near vacuum outside. It must bend at the knee, the elbow, the hip, and the shoulder hour after hour, without leaking at a single seam. It must give the hands enough precision to turn a bolt, seat a connector, or repair a sensor, while still holding pressure against the vacuum pressing in from every direction. Pressure, mobility, and dexterity are all required at once, and each one works against the other 2. The gloves carry the worst of that conflict. Every spacesuit glove built so far draws the same complaint: stiff, tiring, clumsy compared to a bare hand, and the mission asks those gloves to do fine work anyway, seating a connector, turning a small screw, adjusting an instrument calibrated to the millimeter. A task that takes a minute in shirt sleeves back home can take 5 inside a suit. And across years of routine surface work, that difference adds up into real lost time and real fatigue, 1 glove at a time, on every single excursion. The suit also has to survive what the surface throws at it besides physics. It has to hold a stable warm layer across days that swing 60 to 70 degrees. It has to shrug off ultraviolet strong enough to degrade materials built for gentler places. And it has to keep the fine, clinging, perchlorate-laced dust that coats everything outside from ever crossing the airlock threshold, which means careful brushing and decontamination after every single excursion, for years, without one skipped step, Suits built so far were designed for microgravity in low orbit, or for brief trips across a lunar surface. Not this. Not years of daily dust, cold, and radiation together. Not yet. The suit that will actually stand outside on the next world has not been built. It is being designed, tested in analog deserts and on the moon, refined, and still at the point where a crew would need to trust their lives to it. Incomplete. That is only the hours outside. Almost everything else happens inside a second machine, one the crew never fully leaves for 2.5 to 3 years. The habitat. It is where they sleep, eat, work, exercise, and recover, all inside the same sealed volume. And it has to do all of that at once without any of those functions crowding out the others. Here, the very first design decision offers no free option. Fill the habitat to full homeworld pressure, and the crew needs no physiological adjustment at all, sleeping and working exactly as they would at home. But the structure has to hold back roughly a full atmosphere of pressure pushing outward on every wall, the same force pressing in on a diver at the bottom of a 10-meter pool, only aimed the other way. Drop the pressure instead to a third or half of that, and raise the oxygen fraction to compensate, and the walls can be lighter and thinner. The price is a higher fire risk, and a crew that must adapt physiologically to reduced pressure for years. Heavier and safer, lighter and riskier. Choose one. There is no version that avoids the trade. Temperature asks for the same constant attention. Outside, the surface can fall to 80 degrees below zero at night, colder than the coldest night ever recorded on the homeworld's own polar plateau, while inside, crew, lights, cooking, exercise equipment, and life support all generate heat with nowhere to go on its own. Holding a livable range against both directions at once is one of the largest continuous engineering loads the habitat carries. Radiation asks for mass. The same lesson already learned out in the open crossing and echoed again here. Either build the walls thick enough to absorb particles on their own, adding weight the whole way down, or bury the habitat under several meters of soil piled on by robotic equipment before the crew ever lands. Far cheaper in mass, provided that equipment survives its own landing and does its job with no one there to fix it if it does not. Either way, the goal is the same buried quiet that a natural lava tube could offer ready-made, built here by hand instead, meter by meter of piled soil. Then there is simple size. A habitat has to be large enough that years inside it do not become their own slow injury, and small enough to fit inside what a rocket can actually deliver. On the earliest missions, those two demands do not meet comfortably in the middle. The likely result is a floor plan measured in the tens of square meters per person, closer to a small studio apartment than a house, shared with the machines that keep everyone breathing. Growing that space later with inflatable modules or additional landed hardware takes more missions and more years of surface assembly, so the first crews live inside whatever arrives with them, and nothing more for the whole of their stay. And those machines never stop working. On the home world, waste disappears into infrastructure no one has to think about. A pipe, a truck, a system built and buried long before anyone living there was born. Here, everything that enters as food, air, and water has to leave as something. And that something stays inside the same sealed volume unless a system reclaims it. Water recovery from urine already runs near 90% in orbital systems today, 9 cups reclaimed out of every 10, and a next world mission will need to push that figure even higher as resupply grows rare and eventually stops arriving at all. Solid waste asks for the same discipline in a different form, managed and contained without contaminating the habitat around it. A quietly growing volume across 500 surface days that cannot simply be set outside the door. The air asks the same discipline again. Exhaled carbon dioxide has to be pulled out continuously, and rather than simply venting it the way an orbiting station does, a next world habitat can feed that same captured gas back into the reactor that manufactures fuel and oxygen, turning every breath the crew lets go of into part of the cycle that keeps them alive. None of it is finished. A closed loop that holds carbon dioxide, water vapor, oxygen, nitrogen, and every trace contaminant imbalance for years running has been studied, tested in pieces, and never yet proven whole at the scale and for the duration a real mission would ask of it. Everything the crew depends on, every hour of the entire arc, comes down to these two shells, one worn, one lived in, both still short of finished. Beyond them waits a planet with a far older story to tell, one written in rock and dry riverbeds long before any suit or habitat was ever needed. Every one of those systems, the suit, the sealed habitat, the manufactured air, exists to hold back something. And there is a reason that something is there at all. Older than any of the hardware. Older than the mission itself. The next world was not always like this. Orbiters and long-running rovers have spent decades building a slow, patient picture of an ancient world, very different from the one a suited crew will step onto. Once the surface carried liquid water. Once the atmosphere was thicker. Once a churning iron core generated a global magnetic field. A shield much like the one that still wraps the homeworld today. The rock remembers what the surface no longer shows. River valleys run for kilometers with the unmistakable shape of water carving through stone. Outflow channels suggest floods violent enough to fill temporary seas. Layered sediment sits in patterns that, back home, only ever form at the bottom of standing water, held there for a long time. Certain clays and certain salts only form one way, soaking in liquid water for thousands or millions of years. One rover has spent more than a decade working the floor of an ancient crater that once held a standing lake. Another has walked the sediments of a delta where a river once slowed and dropped its silt into open water. A small sample collecting effort has already sealed pieces of that ancient lake bed into tubes and left them waiting on the surface, cached for a future mission built only to bring them home and read what they hold in a laboratory. Here is the part that reframes everything already named. The world did not start out this way. It became this way. It began inside the planet. Every rocky world has a deep interior of slow, churning heat. Material rising, cooling, sinking again, and on the homeworld that churning, paired with rotation, is what generates a magnetic field. The next world had one too, once. The proof is frozen into its oldest rocks. A magnetic fingerprint with nothing left generating it. Billions of years ago, the churning slowed. The next world is smaller, and smaller worlds lose their internal heat faster. The way a small stone pulled from a fire cools quicker than a large one from the same coals. As the interior cooled, the convection driving the field weakened, until one day, gradually and without any single dramatic moment, it stopped. Without the field, nothing stood between the upper atmosphere and the sun. The solar wind, the same steady outward breath of charged particles that a shelter of water and food protects a crew from during the crossing, began striking the atmosphere directly. Over hundreds of millions of years, it stripped the air away, particle by particle, layer by layer, accelerating charged atoms until they escaped the planet's gravity for good. Pressure fell. Water that had been stable as a liquid stopped being stable. Some of it evaporated. Some of it froze at the poles. Some of it sank and froze into the ground, buried and waiting. What was left settled into the thin, cold, brittle envelope. The crew now breathes only through a manufactured system, never through their own lungs alone. Not a badly built world, not a broken one. A world that had what it needed, and slowly lost it. Every hazard already named traces back to that loss. The thin air, the cold, the radiation with no field left to turn it aside, the dryness, the perchlorates in the dust, none of it arbitrary, all of it aftermath. Two worlds, born of the same slow internal physics, ended up in different places for reasons of mass and distance, and how long each one kept its shield. The homeworld is gentle today for one reason only: it has not yet lost what it has. The rest of the surface tells the same deep time story in stone. The interior is layered the way the homeworld's is: thin crust, thick mantle, an iron core, but the crust here is thicker and never broke into moving plates the way the homeworld's did. Nothing recycles, nothing erases. Craters from the earliest bombardments still sit where they fell. Riverbeds still hold the shape of rivers that stopped flowing eons ago. The largest volcanic mountain on the planet rises to roughly 2.5 times the height of the tallest mountain on the homeworld, wide enough to rank among its larger islands. So vast that a climber standing at its summit would watch the ground curve away and vanish below the horizon long before reaching the base. It has been quiet for a very long time, a monument to a phase of the planet's life that already ended. Not far away runs a canyon system longer than the width of one of the homeworld's continents, cut so deep that the homeworld's tallest peaks could stand inside it without their summits reaching the rim. Carved not by any river, but by the slow stretching and cracking of a crust, cooling and pulling apart across billions of years. The next world is a museum of its own past, with almost nothing removed from the exhibit. 2 small moons orbit close overhead, irregular, potato-shaped, likely captured wanderers or the leftover pieces of some ancient collision. One is spiraling slowly inward, and given a few million more years will either strike the surface or shred apart into a thin ring. The other is drifting the opposite way, outward, the way the homeworld's own moon drifts outward a little further every year. Neither change will happen on any calendar a person could hold in mind. Both are already in motion. Whether the ancient, warm, wet version of this world ever supported life is one of the most carefully guarded open questions science is still asking. We don't know yet. The cache samples exist partly to answer it. If the answer turns out to be yes, it means life is not a rare accident but something that starts wherever the conditions allow. And it raises real questions about what it means to bring more life to a place that already quietly had its own. If the answer is no, that matters too. It would mean liquid water and warmth and chemistry are not, by themselves, enough. Either answer changes how a future colony should think about itself. And there is a newer question with no historical answer to draw on at all. Long-term settlement eventually means children born there, not carried there as adults, but raised from infancy in gravity that is only about 1/3 of what a body evolved for. Bones, heart, inner ear, the whole physical sense of balance and weight would develop differently. And no one can say precisely how, because no human being has ever been raised inside partial gravity for a single day, let alone a childhood. Such a person might find a trip to the homeworld exhausting before they even left the ship. The air too thick, the light too bright, standing upright for an afternoon a genuine strain. They might never make the trip at all. Not a visitor born far from home. A person for whom the next world simply is home, the first of a kind that has never existed before. Terraforming sits at the far edge of that same long arc, a slow-motion answer to almost everything already described. The basic physics is understood. Frozen carbon dioxide waits at the poles and in the soil, and warming it releases more atmosphere, which traps more heat, which frees more frozen gas, a loop that in principle could feed itself. Proposals exist, orbital mirrors to focus extra sunlight on the ice caps, manufactured greenhouse gases, redirected comets carrying water and volatiles, from the outer solar system. None of it has been ruled out by physics. But physics is not the obstacle. Time is. Not one lifetime, not 10. Thousands of years. Longer than the span of every recorded civilization stacked end to end, before the transformation would mean anything at the surface. And even after all that time, the same problem that unraveled the original atmosphere would still be waiting. Without a magnetic field, any new atmosphere would eventually be stripped away, exactly as the first one was. A proposal exists to place an artificial magnetic shield in space between the planet and the sun, deflecting the solar wind before it ever reaches the air below. But that idea remains a sketch on a drawing board, decades or more from anything resembling engineering. Terraforming will not change what the first crews face. It is not a plan. It is context, a reminder that the brutality has a shape that could, in principle, soften over time, just not on any clock that helps the people who have to live inside it now. The world's entire story runs in one direction, warmth to cold, thick air to thin, shielded to exposed. Every hardship already named is the last chapter of that story, still being written on the surface today. What was left to ask is whether a story that long can still leave room for something new to begin. That question does not belong to the deep past anymore. It belongs to the people alive today, and the honest answer is steadier than the long catalogue might suggest. Every item in that catalogue is real. The airless cold, the poisoned soil, the radiation with no field left to turn it aside, none of it was invented or exaggerated for effect. Each is a measured consequence of physics, biology, and a planet's long history checked against instruments, not guesswork. And yet knowing all of it in this much detail turns out not to be a source of dread. It becomes instead a source of clarity. No human being has stood on that surface yet. Not for lack of ambition, not for lack of funding, not for lack of will. The reason is a list, specific and long, and every item on it already has someone working on it right now in a lab or a test facility somewhere on the home world. The work is not waiting on one lucky breakthrough. It is happening in dozens of places at once, in different languages, on different clocks. Engineers are testing landing systems built to slow heavy payloads through an atmosphere too thin to help much on its own. Physiologists are studying what months of weightlessness do to bone and blood and eyesight, and building the treatments meant to slow it. Life support engineers are pushing water and air recycling closer to complete, cycle by cycle. Geologists are combing years of orbital data for buried ice, for open lava tubes, for landing sites that sit near resources a crew could actually use. Nuclear engineers are running ground tests on compact reactors, working through the safety reviews a reactor needs before it is trusted to fly. Physicians are building tools that let a surgeon on the homeworld guide a crewmate's hands across a delay of many minutes. None of this is a single project. It is many small patient projects converging. Here is the part that reframes the whole catalogue. What has kept a human being off that surface was never a failure of nerve. It has always been a queue of separate, solvable problems, each one measured, each one already assigned to someone. None of this is new. Every outward step a person has ever taken looked, in its own time, exactly this hostile. Think about the first people to paddle small rafts across open water toward islands they could not yet see, with no rescue waiting and no map, only the stars and the pattern of the swell. Some of those crossings ended in loss, others ended in new shorelines, and generations of lives that followed. The first long ocean crossings under sail used ships that would today be judged dangerously crude, and still reach continents no one aboard had ever imagined. The first balloons and the first aircraft lifted people into open sky the body was never built for, on instruments barely tested, and sometimes it went wrong. And the first crewed spacecraft left for an environment harsher in some ways than the next world's own surface. No air pressure at all outside the hull, unfamiliar radiation, wide swings of heat and cold, and still the missions flew, and the crews came home, carrying forward decades of knowledge. The next step now leans on. Every one of those steps looked impossible before it was tried. Everyone was carried by patient people solving one specific problem after another, and every one of them quietly became ordinary for the generation that followed. The next world is a harder step than any of those, but it is being approached with more knowledge, more tools, and more people working on it at once than any earlier step ever had. Some of that progress is arithmetic, plain and countable. Large, reusable launch vehicles, developed over the past decade or two, are built around a different question than any rocket before them. Not how to fly one dramatic mission, but how to fly cargo again and again, cheaply enough to matter. If those vehicles work as designed, at the scale their builders intend, the cost of putting a kilogram of payload onto that distant ground could fall to a fraction of any historical price. That single number is what makes a long-term human presence something that can be planned for, rather than only imagined. And the robotic exploration of the next world no longer belongs to one country alone. Orbiters, landers, and rovers now carry the markings of a growing list of nations, several of them already speaking, in public, about crewed missions of their own. None of that solves the engineering by itself. All of it adds hands, and money, and momentum to the same slow project. There is a nearer, quieter piece of this progress overhead every night. The homeworld's own moon plays a specific, practical role in getting ready, one often mistaken for a distraction. Landing there and lifting off again uses nearly the same skills the next world will demand. Precise guidance, careful propulsion, protection from dust, movement in reduced gravity, and it can be practiced only 3 days from home. Not the better part of a year, where a crew in trouble can be brought back within days rather than months. The moon also holds its own buried water ice, frozen for billions of years in craters the sun never reaches. And pulling that ice out, splitting it, and using the oxygen is the same basic chemistry the next world will need. Tested somewhere, a mistake does not have to be fatal. Nothing built on the moon can simply be lifted and carried onward, but every lesson learned, there travels with the people who learned it. None of that makes the honest gaps disappear, and naming them plainly is not pessimism. It is precision. First, no one has yet built and proven a landing system that can bring a crew-scale mass safely to that surface. Second, no one has yet run resource production at anywhere near the scale a real crew's survival and return would require. Third, no one has yet kept a human body healthy across the full combined length of the crossing and the stay together. Fourth, no one has yet closed the loop on air and water and waste, fully and reliably, for years at a stretch, anywhere but on paper and in short trials. 4 gaps, not 4 failures, 4 items still open on the same long list as everything already named, being worked on by the same patient people. Picture then what a first success actually looks like. Stripped of spectacle. A crew of perhaps 4 leaves the homeworld atop a vehicle already being built and tested today. They spend weeks in orbit finishing preparations and then depart. For 6 to 9 months they coast, exercising, eating, sleeping, reading, talking to the people they love through messages that arrive minutes late, watching a familiar blue point shrink behind them while an unfamiliar orange one grows ahead. They arrive, they descend, they land. They spend a few days simply adjusting to lighter footsteps and a stranger sky, and then they begin the work. Sampling, building, measuring, learning what only a hand on the ground can learn. 500 days pass this way, one season sliding into the next, dust storms rising and settling, polar caps shrinking and returning, and every so often, low over one horizon or the other, that same small blue point climbing into view, holding everyone they have ever loved. Then they leave. Another 6 to 9 months of coasting carries them home, and when they finally step out again into open air, they are the first human beings to have stood on a planet with its own seasons, its own weather, its own billion-year story, and returned to tell it. None of it will look like the sudden, triumphant instant so many pictures have promised. Not sudden, not triumphant. Slow instead. Patient instead. Years of unglamorous work by people whose names most of us will never learn, in labs and test stands and mission control rooms, solving one measured problem after another until the list is finally short enough to fly. Somewhere ahead, on a date not yet written on any calendar, someone will step down onto a cold, thin, pink-orange morning, onto dust that has not been disturbed in billions of years. That step will not erase the brutality. The cold will still be there. The thin air will still be there. The catalogue, every honest item of it, will still be true the next morning, exactly as it always has been. But for the first time, none of it will have been enough to stop the step from being taken. That is the whole shape of the story, its brutality and its hope held in the same hand. What comes after that first footprint will matter more than the footprint itself. The slow work of turning a shelter into a home. Children raised under a sky their parents once needed a suit to stand beneath. A small, stubborn human presence taking hold on a planet that spent billions of years losing everything it once had. It is not a mission anymore at that point. It is a beginning, measured in centuries, and it starts with the quiet, patient work already happening tonight in rooms most of us will never see.